Now let's continue our discussion in chapter 7. Last time we look at the um, distribution of the binomial and case where you have a nice bell-shaped curve like this. You can either look at the book or this Gaussian R, and also we look at the mean and also the standard deviation. The mean is actually about 12.5, and the standard deviation is 1/10. So in reality, we can also look at a smoothed version of this. And if we set the mean equals 0 and the standard deviation equals 1, we're going to have what we call the standard normal distribution. So by definition, we're going to have the mean equals 0 and the standard deviation equals 1. So this is the shape of the curve is look like a bell-shaped and kind of like another version of this graph. And also notice that even though this graph looks like it almost touches, or maybe it already touches the z-axis, actually it doesn't. It just gets really, really close. Theoretically speaking, the graph will always be above the z-axis or the horizontal axis. But practically speaking, when when the absolute value of z is getting larger, this graph is be so close to the z-axis that you can't really tell the difference using your naked eye. Now, the total area under the curve is equal to 1. That represents the total probability of all the possible events. And if you restrict to a portion of the graph, such as the portion between z equals 0 and z equals 1, and we can find the area which is approximately 0.34. Well, you may wonder, how do we find this area? Well, if you know calculus, this area can be found using calculus. Of course, we don't do it in this course. And if you know how to use R, of course, we'll later introduce our R command to find this area. Or there are also some tables that people made for this purpose. You can also using those tables to find the area. But anyway, this area corresponds to the probability, namely the probability for the z value to be between 0 and 1 is approximately 34%. Now, here's the table 7.2. You can find the same table on page 173 from your book. And this will tell you the area under the curve between 0 and some values of z. For example, if you set z equals 0 and z equals 1.3, so you look for 1.3, that corresponds to 0.403. So here, the probability between z equals 0 and z equals 1.3 is 0.403. And similarly, by symmetry, the probability between z equals negative 1.3, which is about here, and z equals 0 is also the same number. And adding these two areas together, you get a probability between z equals negative 1.3 and z equals positive 1.3 is 0.6806. You just add these two numbers together. And now here are some useful commands to find the probability of z equals certain values. So for example, we can use this pnorm command. And so here, the first value is the z value, and then you need to specify the mean is 0, standard deviation equals 1. This corresponds to the standard normal distribution. And then the value is about 0.90. Notice that this is not the exactly same thing, not exactly the same thing as we have seen from the previous page. The reason is because this command pnorm gives you the area, the total area, including the left half. So the total area from negative infinity all the way to this vertical line at z equals negative positive 1.3. And therefore, if you want to find this shaded area, and you can just subtract your result by half. That's because the total area under the curve is 1. By symmetry, the left half has the area 1/2. And therefore, if you do this command and then minus 0.5, you're going to get 0.403-ish. And that corresponds to this 0.403 in the table. So this will give you the probability and between z equals 0 and z equals 1.3. And if you want to find the probability of z being greater than or equal to 1.3. So all you can do is to use 1 minus the probability. So you're going to use 1 minus the probability when z is less than or equal to 1.3. So this will give you 0.0968. So this is the probability for z being greater than or equal to 1.3. So those are the useful arguments, and you can go back to it. And now here's the thing. Not every normal distribution is standard. Namely, the mean is not necessarily 0 and the standard deviation is not necessarily 1. And in order to accommodate this, we introduce what we call the standard score. The idea for the standard score is that if you have a variable x and we know the mean is supposed to be mu, that's the Greek letter mu, and the standard deviation is sigma, that's another Greek letter. And then what we do is we subtract the mean from x, and then we divide the whole thing by sigma. We divide the whole thing by sigma. So this will give you the standard score. You can prove that if x follows some kind of normal distribution, not necessarily standard, and then its z-score will follow a standard normal distribution. So here, for the binomial p bar, the standard score is given by this because x is p bar, the mean is p, and sigma is the standard distribution, the standard deviation defined before. And now these z-scores will have the mean 0 and the standard deviation 1. So now we can have the standard normal distribution. Let's take a look at an example. Suppose you have n equals 4 and p equals 1/2. Better, but let me just write down. Let me just write down this this on my whiteboard. And here is my dearly beloved whiteboard. So we're going to have z equals p bar minus p, and then divides by the square root of p times 1 minus p divides by n. So this is the z-score formula. So in our next example, we're going to use the binomial when n equals 4 and p equals 1/2. So basically, think about this as you flip the coin, a fair coin 4 times. And now we're going to look at this distribution right here. Of course, if you flip a coin 4 times and you can get 0 heads or 1 head or 2 heads or 3 heads or 4 heads. So if you get 0 heads, the p bar value is equal to 0. And if you get 1 head, the p bar value is 1 out of 4. If you get 2 heads, it's 1 out of 2, which means 2 out of 4 is 0.5, and so on. So now we want to find, we want to compare the area under the standard normal distribution that is associated with the p bar value equals 0.75. So this is the p bar value, and we want to find the area under the standard normal distribution. And so here is what we can do. So now, first of all, we calculate the sigma, which is the denominator here. Sigma, in this case, is equal to the square root of p is 1/2, because it's a fair coin, and 1 minus 1/2. And then the small n equals 4. So this will simplify to 0.25 or 1/4. And for this p bar value equals 0.75. That's this p bar value right here. We can calculate the z value, which is 0.75 minus 0.5, that's the true value, over sigma, which is 0.25. So, and it turns out that this value is precisely 1. So this is the z value corresponds to the p bar value equals 0.75. Now we're going to do two things. The first thing we're going to do is to find the area to the left of this line, z equals 0.75. Imagine that I have a line here, and see if I can draw a line here, and imagine that I have a line here at z equals 0.75. And then I can calculate the area. I can calculate the area to the left under the curve to the left of this line. So to the left of this line. So here is the so this. Oops, I don't mean to do that. Let me cancel this line. Okay, I just mean to draw a horizontal and vertical line at z equals 0.75. So this is I mean at the p bar value equals 0.75, that corresponds to z equals 1. Now, what we're going to do is to calculate, is to compare that the value here to the left of this line under the curve, and also to the value of the total height of all those rectangles. And we can use R to make our life much simpler, even though there's nothing wrong if you want to use a table. It just works equally, right? So for the area under the curve, we're going to choose 1. I mean, we're going to use the P norm of 1 here because the z value is 1, mean equals 0, standard deviation equals 1. So here, this is 0.841. So here, the area under the curve, let me go back to this my whiteboard. And so here, the area of this shape under the curve and here is let's go back to R and check our results. So our result shows that it is 0.841. So it's about 0.841. So let's go back to our whiteboard, and it's 0.841. Now, what we can do is also do the area of like the total of all those vertical bars except for the last one. So we're going to do these 4 vertical bars. And you can see, as you can see from the graph, if you just consider the total region consists of the first 4 vertical bars, that's kind of had a similar area as the curve, as the region under the curve, and to the left of z equals 7.075. So let's do this area. Again, we're going to use R to make our calculation simpler. So we're going to use here we are define another variable that's called x, and it's defined as the vector between 0 and 3, because this is kind of like one head, and I mean 0 heads, 1 head, 2 heads, and 3 heads. And now we're going to do the sum of the d by norm of x, and of course this time we, instead of doing 25 times, we're going to just do 4 times. So this area is approximately 0.93. So it's approximately 0.93. So this is the area to the left of this. So here it's equal to 0.93. So this is our 0. Actually, let me be a little bit more accurate. The answer is 0.9375. So let's just be a little bit more accurate. 0.9375. So this is the comparison. Of course, you may say, hey, these results are not quite close. The answer is that's true. That's true. However, what we can also do is to find the z value. Let's just do 1 bar, and let's just focus on 1 bar. And if we use this same idea of calculating the area of 1 bar and compare that with the area under the curve. So basically what I'm comparing is, let's focus on the 1, 2, 3, 4, the 4th bar over there. So the 4th bar there. So the 4th bar is like this. Okay, this is the fourth bar. And now let's compare that area with the area under the curve between these two values. So this is what we are comparing. So we're comparing two areas. The first one I'll shade it with red. Another one I'll just shade it with this mysterious color. And you see these two areas are not identical, but they're similar. So if we compare these two areas, and we should get some similar answers. Again, we use similar R codes. And notice that here, if you want to do the Z value for the left boundary, you can do the calculation and get 0.5. And right boundary is 1.5. You can to do this, you need to take the average between 0.5 and 0.75, which I believe is 0.625. So here, the new Z value is for the left boundary is if you do 0.625, which is the average between 0.5 and 0.75. That's the middle line here. And then minus 0.5. And then over 0.25, we're going to get 0.5. And similarly, you can do the other average. So this will give you 0.875, and minus 0.5. And then over 0.25. So in this case, we're going to get 1.5. So we're going to basically find the area between these two Z values under the curve. Again, we're going to go back to our R, and we're going to do this. And the P norm of 1.5 and minus, let me just copy and paste this. And I'm going to change it 1.5 to 0.5. So this is what we're going to get. We're going to get about 0.242. So it's approximately 0.242. So here is the 0.242 is this area. Okay. And now, how about this part, the third vertical bar? Well, again, you can use R to find out, and that's actually the fourth vertical bar. So what you can do is to do the sum, is do the D by norm, and we don't need to do sum because there's only one term. And here, X, the value is equal to 3. So we just do this. That's the probability of getting 3 heads. We're going to get 0.25. So you see these two values are really close to each other. So this one will give you the value 0.25. And so these two areas, one is the area of the region under the curve between these two vertical lines. It's this one right here. Another one is just this rectangle right here. They have very, very similar areas. So that's why we can use one to approximate the others. And so here's the solution. And first of all, we find the standard deviation, and then we can find the standard score for p bar equals 0.75. And also we can find the standard score when p bar equals 0.625 and p bar equals 0.875, etc. And then you can use the R to find out. So this is the command, and then you can compare that with the binomial distribution. All right, so this is another example, but now instead of having p equals 1/2 as we always do, we're going to now have n equals 12 and p equals 1/4. So you can think about this as an unfair coin. What I mean by that is we can make a coin in such a way that one end, one side, one face is heavier than the other. So when you flip the coin, you can only get 1/4 of the chance to get a head, and the other 3/4 of the chance you get a tail. So basically the distribution will now look like this. And now we want to compare the binomial probability of 3 or more successes with that given by the normal approximation. So we're going to do two things. And so we're going to do the binomial and with the normal, and we should get some very similar results. So let's take a look at the solution. And so first of all, in this question, P is 0.25 and equals 12. And we want to consider P bar value is 2.5 over 12 is 2.5, because if you want to say 3 or more, you see here, this vertical bar actually starts from this middle line, which is 2.5. It starts from 2.5 over 12 instead of 3 over 12. So its p bar value is 2.5 over 12. And then you can calculate the z-score for that number is negative 1 over 3. So the z value is a negative number. So in this case, the z value for this vertical bar is a negative 1/3. And then we just need to run. So we need to run 2 commands. And the first one is here you can use 1 minus the p norm and of negative 1 over 3. So this will give you 0.63. So 0.63 is the area under the curve, of here. So it's this area of this tail under the curve, starting from this line right here. It's 2.5 over 12. And now we can also consider the total of these rectangles and we add them together. So to do so, we're going to define x as defined. Here's another way to write a vector. You can simply, instead of using c, you can also just use 3 through 12. And you can actually quote x to make sure. And then you can do the sum of the b by norm of x, comma 12, comma 0.25. 12 because we flipped the coin 12 times. 0.25 is the probability of getting one success. And if you flip once, and you get 0.61-ish, 0.61-ish. So if you compare these two results, you see you get very similar. They are not identical. There is a bit difference, but this is only approximation. So this will give you an idea how we can approximate the binomial distribution, which is those rectangles or the histograms, by the normal distribution, which looks like more smooth. Again, they don't give you exactly the same area, but they are similar. So this is the idea. There's another normal table, which I don't think is particularly important, but basically this one will give you the area between negative z and z. For example, when z equals 1, you get 0.683. This really tells you the area between z equals negative 1 and 1 is 0.863. And that's it. I don't even recommend using it because first of all, you have the other table. You can simply find the correct value and multiply by 2 to get a value. And secondly, you have R, which is extremely convenient to use. There's another small topic that we can cover in this chapter, but we'll wait until our next video. Thank you very much for watching, and I will see you in the next video.